Now exercise 4.14. Two concentric circular coils X and Y of radii 16 centimeter and 10 centimeter respectively lie in the same vertical plane containing the north to south direction. Coil X has 20 turns and carries a current of 16 ampere. Coil Y has 25 turns and carries a current of 18 ampere. The sense of the current in X is anticlockwise and clockwise in Y. For an observer looking at the coils facing west, give the magnitude and direction of the net magnetic field due to the coils at their centers. Now see here, the radius of coil X and Y are given to you 16 centimeter and 10 centimeter. So we can take radius of X Rx, that is 0.16 meter, radius of Y Ry, that is 0.1 meter. Number of turns in X, that is Nx equal to 20. Number of turns in Y, that is Ny equal to 25. Current in X coil, Ix equal to 16 ampere. Current in Y coil, Iy equal to 18 ampere. This data is given to you. Now both are concentric. Current through both the coils, that is in mutually opposite direction. It implies that the magnetic field produced by both the ring, that will be mutually opposite at their centers. So first of all, we can calculate the magnetic field at the center of the current carrying loop by equation B equal to mu 0 Ni upon 2R. So for X ring, we can write Bx equal to mu 0 Nx Ix upon 2Rx. Substitute the values. Mu 0, that is 4 pi into 10 raised to minus 7, Nx 20, Ix 16, 2, radius of X 0.16. Now solve this one, you will get the answer. And with the help of right hand thumb rule, you can decide the direction. So due to X coil, it will be towards west. Similarly, calculate the magnetic field of Y coil, that is By equal to mu 0 Ny Iy upon 2Ry. Now mu 0, that is 4 pi into 10 raised to minus 7. Ny, number of turns in Y 25. Current in Y, Iy, that is 18 upon 2 into radius of Y, that is 0.1. And now solve this one, you will get the magnetic field due to coil Y. This will be towards east, opposite to this one. Now here you can observe this thing, By, that will be greater than Bx. So resultant magnetic field will be By minus Bx. So take the difference of these two fields, and resultant field, that will be towards the east because By, that is dominant to Bx. Clear to all of you? 4.15. A magnetic field of 100 Gauss, 1 Gauss, that is equal to 10 raised to minus 4 Tesla is required, which is uniform in a region of linear dimensions about 10 centimeter and area of cross section about 10 raised to minus 3 meter square. The maximum current capacity of the given coil of wire is 15 ampere, and the number of turns per unit length that can be wound around a core is at most 1000 tons per meter. Suggest some appropriate design particulars of a solenoid for the required purpose. Assume the core is not ferromagnetic. Now, required magnetic field, that is 100 Gauss. So 100 into 10 raised to minus 4. So that is 10 raised to minus 2 Tesla. Now maximum current capacity, that is 15 ampere, and maximum possible number of tons per meter, that is 1000. This one is given to you. Now the magnetic field at any point inside the solenoid on its axis, that we can write B, that is mu 0 n I. Now Ni, that is equal to B upon mu 0. B, that is 10 raised to minus 2 required magnetic field. Mu 0, that is 4 pi into 10 raised to minus 7. And now if you solve this one, your answer will come to 8000. So when your n into I, that is 8000, it implies that here you have to make the combination of n and I in such a way that your answer, that should be 8000. So suppose we take current I, that is 10 ampere, and number of tons 800 per meter, then we will get Ni, that is equal to 8000. And here see the current that is less than its maximum capacity, as well as the number of tons that is also less than its capacity. So this is the suggested configuration. Okay, but see here, you can suggest like this also. The core length may be 50 centimeter, having 400 tons, and suppose take cross section, that is this much. Then also you can do the same thing. Clear to all of you? 4.16. For a circular coil of radius r and n turns carrying a current I, the magnitude of the magnetic field at a point on its axis at a distance x from its center is given by B equal to mu 0 I r square n upon 2 into x square plus r square raised to 3 by 2. Question A. So that this reduces to a familiar result for field at the center of the coil. B. Consider two parallel coaxial circular coils of equal radius r and the number of turns n carrying equal currents in the same direction and separated by the distance r, so that the field on the axis around the midpoint between the coils is uniform over a distance that is very small compared to r, and is given by B equal to 0.72 mu 0 n I upon r approximately. Such an arrangement to produce a nearly uniform magnetic field over a small region is known as Helmholtz coil. Okay. Now, first question A. So, equation of the magnetic field at any point on the axis of the current carrying coil, that is given by mu 0 I r square n upon 2 into x square plus r square raised to 3 by 2. Now, at the center of the coil, we can take the distance of the point from the center of the coil, that is 0, means x equal to 0. So in this equation, if we substitute x equal to 0, then we will get B equal to mu 0 I r square n upon 2 into 0 plus r square raised to 3 by 2. Now here this r square raised to 3 by 2 will resultantly give you r cube. And now if r square cancel, then 1 r will be there in denominator. So your equation turns to n mu 0 I upon 2r. This is the equation for the magnetic field at the center of the current carrying coil. Clear to all of you? Now question number B. So here we have two coaxial coils having radius that is equal to r, number of turns in each that is n, and these two are separated by distance r. Now we have to prove this thing. Now at the midpoint of the axis of these two coils, right, the magnetic field that is uniform in the region close to the midpoint. Okay, now see here, midpoint means from each coil it is at distance r by 2. And now we have to consider another point which should be very close to this midpoint. So here consider that another point at a distance d from the midpoint as shown in the figure. It implies that now from the center of the first coil, our decided point that will be at distance r by 2 plus d, and for second one it will be r by 2 minus d. Now in our equation, mu 0 I r square n upon 2 into x square plus r square raised to 3 by 2, in that equation x is replaced by r by 2 plus d for first coil and r by 2 minus d for second coil, and mu 0 I r square by n, that is common from the equation of fields of both the coil, current through both the coil that is in the same direction, so field at the axis will be in the same direction. So resultant field, that is the summation of these two, and this denominator part that is written in the numerator, so its power is taken as raised to minus 3 by 2. Clear up to this one? Now mu 0 I r square n by 2 outside the bracket as it is. Now simplify this, r by 2 plus d whole square as r square by 4 plus rd plus d square plus this r square as it is and whole raised to minus 3 by 2. Plus now simplify this, r by 2 minus d whole square as r square by 4 minus rd plus d square plus r square raised to minus 3 by 2. Now mu 0 I r square n by 2 as it is, this r square by 4 plus r square, that you can write as 5 r square by 4 plus rd plus d square as it is, and raised to minus 3 by 2. For this second bracketed term, you can write again r square by 4 plus r square, that is 5 r square by 4 minus rd plus d square as it is, and this whole raised to minus 3 by 2. Now mu 0 I r square n upon r, that is as it is. Now from these two terms, suppose we take 5 r square by 4 common. Now if we take 5 r square by 4 common, then at the place of 5 r square by 4 you can write 1. For this rd, now from rd if you take 5 r square by 4 common, then you have to multiply it by 4 upon 5r, because see, if you multiply this 4d upon 5r by 5r square upon 4, then again you will get your answer rd. And here in the question itself it is given to you in the region very close to the midpoint. We have to derive the equation for magnetic field. means D that is very small compared to R, and therefore D square is neglected compared to other terms. Clear to all of you up to this one? Now, mu 0 I R square n by 2. Now, here this R square raised to minus 3 by 2 will give you R raised to minus 3. So when you write it in denominator, then that will be R cube. And this 5 by 4 raised to minus 3 by 2. So you can write it as 4 by 5 raised to 3 by 2. Now, here for these bracketed terms, you can use binomial theorem for simplification. Now, in binomial theorem, the power is multiplied with this second term. So, 1 minus 3 by 2 into 4D upon 5R plus this 1 and minus 3 by 2, so plus 3 by 2 into 4D upon 5R. So see here, minus 3 by 2 4D upon 5R and plus 3 by 2 4D upon 5R. These two will be cancelled. And this 1 plus 1, that will be 2. So you can write mu 0 I n, this R square upon R cube, that is R, these 2 as it is, 4 by 5 raised to 3 by 2, 2 cancelled. So mu 0 I n upon R into 4 by 5 raised to 3 by 2. And now if you solve this term, 4 by 5 raised to 3 by 2, then it will come to approximately 0.72. 4.17. A toroid has a core non-ferromagnetic of inner radius 25 centimeter and outer radius 26 centimeter, around which 3,500 tons of wire are wound. If the current in the wire is 11 ampere, what is the magnetic field? A, outside the toroid, B, inside the core of the toroid, and C, in the empty space surrounded by the toroid. Now see here, inner radii, that is 25 centimeters, say that is R1. Outer radii, say that is R2, 26 centimeter. Total number of tons wounded, that is 3,500. Current passed, that is 11 ampere. So here, if we consider the Amperian loop as the axis of the toroid, then the radius of that Amperian loop, that will be R1 plus R2 by 2. Say that is R. So 25 plus 26 by 2, we will get 25.5 centimeter. So R will be 25.5 into 10 raised to minus 2 meter. Now, here the number of tons per unit length will be total number of tons divided by total length for the Amperian loop, and that is 2 pi R. So 3,500 upon 2 pi 3.14 R, that is 0.255. So you will get the number of tons per unit length. Now, magnetic field outside the toroid, we discussed in the theory, that is equal to 0. Then after inside the core, so that is B equal to mu 0 Ni, mu 0, that is 4 pi into 10 raised to minus 7. Substitute the value of small n, which we calculated here, and I, that is 11 ampere. Solve it, you will get value of B. inside the core. Then field in the space surrounded by the toroid, that is also 0. In theory, we proved this thing. Clear to all of you? Example 4.18. Answer the following questions. A magnetic field that varies in magnitude from point to point but has a constant direction east to west is set up in a chamber. A charged particle enters the chamber and travels undeflected along a straight path with constant speed. What can you say about the initial velocity of the particle? So when the charged particle is moving undeflected, it implies that the magnetic force is not acting on it. Now, we know this thing. When any charge Q is moving in the magnetic field B with velocity V, the force acts on it, that is QVB sine theta. Means if the speed and magnetic field are either parallel or anti-parallel, then theta will be either 0 or pi. In that case, the force will be 0 and the particle will move undeflected. So initial velocity or speed, we can say that should be parallel or anti-parallel to B. Question B. A charged particle enters an environment of a strong and non-uniform magnetic field, varying from point to point both in magnitude and direction, and comes out of it following a complicated trajectory. Would its final speed equal the initial speed if it suffered no collision with the environment? So here see, if the magnetic field that is uniform or non-uniform, whether it is changing point to point both in magnitude or direction or not. But when any charged particle is moving in the magnetic field B with velocity V, the force which acts on the particle, that will be always perpendicular to V and B, because direction of F, that is in the direction of V cross B. Now when force is perpendicular to the velocity, then in that particular case, the work done, that will be always 0. In standard 11th, we studied this thing. And as per work energy theorem, when work done that is equal to 0 means change in kinetic energy, that is also 0. So if change in kinetic energy, that is 0, means the speed remains constant. So we can say the final speed, that will be equal to initial speed. Clear? Now see the particle that is electron, that is negatively charged particle. And we know this thing, when negatively charged particle is under the effect of the electric field, the force acts on it in the opposite direction of electric field. So here, due to electric field, the force on electron, that will be towards the north. It implies that here magnetic field should be applied such that the force on electron due to magnetic field, that should be in southward direction. Okay. Now, your force, that should be southward. So here, if we think about the direction of magnetic field, now suppose direction of the magnetic field that we take vertically upward, then as per Q into V cross B, if you rotate right-handed screw from V to B, then your thumb will point northward. But that is for charge Q. Here electron is negatively charged particle. So the force that will be in opposite direction. So if your magnetic field that is vertically upward, it implies that perpendicular to the plane of paper in outward direction, then the electron will experience the force in downward direction. And now if these two forces due to electric field and due to magnetic field are balanced, then it will move undeflected. Clear to all of you? Example 4.19. An electron emitted by a heated cathode and accelerated through a potential difference of 2 kilovolt enter a region with uniform magnetic field of 0.15 Tesla. Determine the trajectory of the electron if the field A is transverse to its initial velocity, B makes an angle of 30 degree with the initial velocity. Okay. Now see, the potential difference of 2 kilovolt means 2 into 10 raised to 3 volt. That is given to you. And electrons emitted by the heated cathode are accelerated by this potential difference. And then after entered in the region, which one is with magnetic field B equal to 0.15 Tesla. Now we know this thing. If the charged particle enter to the magnetic field perpendicular to it, means initial velocity is transverse, right? In that particular case, particle will execute circular motion. And if the particle enter in the magnetic field with velocity at some angle, then it will execute helical motion. Okay. So here, if you want to find the trajectory, means radius for the motion of the charged particle, then you must have its velocity. But velocity is not given to you. So see, we know this thing. In second chapter, we studied when any charge Q is accelerated with the potential difference of V volt, then energy gained by it, that is QV. Here, electron is accelerated, so energy gained by electron, that is EV, and that is in the form of kinetic energy. So that is equal to half mv square. If we make V as a subject of equation, then that is under root 2 EV upon ME. Substitute the values to E, that is 1.6 into 10 raised to minus 19, V, that is 2 into 10 raised to 3, upon mass of electron, that is 9.1 into 10 raised to minus 31 whole raised to 1 by 2. Okay. Now solve this one. You will get the velocity of that particle. Now, in first case, the particle executes circular motion and radius of its circular path, that is given by mass into velocity upon EB, MEV upon EB. Substitute mass of electron, speed which we calculated here, charge of electron B 0.15 Tesla, that is given to you. Then solve it, you will get the radius of the circular path. Then in second case, when the velocity is making an angle 30 degree with the field, then the motion that will be helical one, and the radius of the helix, that is R dash equal to mv sine theta upon EB. See, mv upon EB that you calculated here, sine theta, that is sine 30. that is 1 by 2, means your R dash, that will be R by 2. So calculate it, you will get the answer. Clear to all of you? 4.20. A magnetic field setup using Helmholtz coils is uniform in a small region and has a magnitude 0.75 Tesla. In the same region, a uniform electrostatic field is maintained in a direction normal to the common axis of the coils. A narrow beam of single species charged particles, all accelerated through 15 kilovolt, enters this region in a direction perpendicular to both the axes of the coils and the electrostatic field. If the beam remains undeflected, when the electrostatic field is 9 into 10 raised to minus 5 volt per meter, then make a simple guess as to what the beam contains. Why is the answer is not unique one? See, magnetic field given to you, that is 0.75 Tesla. Electric field, that is 9 into 10 raised to minus 5 volt per meter. Okay. And the charged particles in the beam are accelerated by the potential difference of 15 kilovolt. So that is 15 into 10 raised to 3 volt. Now it moves undeflected. It implies that velocity, that is E upon B. So that is 9 into 10 raised to minus 5 upon 0.75. You will get the answer 12 into 10 raised to minus 5 meter per second. Now here we have to find which particles are there in the beam, what the beam contains. So when any charged particles accelerated with the potential difference of V volt, the kinetic energy gained, that is half mv square, that is q into V. Now to find out the type of particle, calculate its specific charge, means q by m. So here q by m, that is V square by 2V. V that we calculated 12 into 10 raised to minus 5 whole square upon 2. V that is 15 into 10 raised to 3. Solve it, you will get the answer this much coulomb per kilogram. Then you have to check this thing for which particle q by m have this particular value. So that is for deuteron and Li plus 3, right? So when you are getting q by m for two type of different particles, then we can say the answer that is not unique one. Clear to all of you? 0.21. A straight horizontal conducting rod of length 0.45 meter and mass 60 grams is suspended by two vertical wires at its ends. A current of 5 ampere is set up in the rod through the wires. A. What magnetic field should be set up normal to the conductor in order that the tension in the wire is 0? B. What will be the total tension in the wires if the direction of current is reversed, keeping the magnetic field same as before? Ignore the mass of the wires, and G, that is 9.8 meter per second. Now see, length of the rod, that is 0.45 meter, mass of the rod, that is 60 gram, that is 60 into 10 raised to minus 3 kilogram, and the current passed through it, that is 5 ampere. Now see, as shown in the figure, if with the help of two wires from the rigid support, the conducting rod that is suspended, then its weight will be vertically downward. And suppose the tension in the wires, that is T in each wire. Now, what magnetic field should be set up normal to the conductor in order that the tension in the wires is zero? Now, if the weight of the rod becomes zero, then tension in the wire will be zero. It implies that we have to set up the magnetic field such that the force on the rod ILB, that should be vertically upward, and it should be exactly equal to mg. So for tension in the wire to be zero, ILB, that should be equal to mg. So B, that is mg upon IL, mass that is 60 into 10 raised to minus 3, G that is 9.8, I that is 5 ampere, and length of the rod 0.45. Solve it, you will get the magnitude of the magnetic field which should be applied here. Now see the question B. In that it is given to you the direction of current is reversed. Now, if the direction of current is reversed, then definitely the force ILB, that will be also reversed. So, in the second case, we can say the force ILB and mg both will be in the same direction, downward. So, tension in the wire, say that is TT. So, we can write total tension, that is 2T equal to ILB plus mg. But magnitude wise ILB and mg, that is same, so we can write 2mg. So 2 into m, that is 60 into 10 raised to minus 3, and g, that is 9.8. Solve this one, you will get the total tension in the wires. Clear to all? 4.22. The wires which connect the battery of an automobile to its starting motor carry a current of 300 ampere for a short time. What is the force per unit length between the wires if they are 70 centimeter long and 1.5 centimeter apart? Is the force attractive or repulsive? Now see the current, that is 300 ampere, length that is 70 centimeter, so 0.7 meter, and R means separation, that is 1.5 centimeter, so that is 1.5 into 10 raised to minus 2 meter. Force between two parallel current carrying wires, that is mu 0 I1 I2 L upon 2 pi R. Substitute the values. Now, force per unit length, so take L on left hand side, F by L mu 0 I1 I2 upon 2 pi R, mu 0 4 pi into 10 raised to minus 7, I1 300, I2 300, 2 pi R, that is 1.5 into 10 raised to minus 2. Solve it, you will get the answer. Now here, the force that will be attractive or repulsive. So force will be repulsive one, because through one wire the current will move in forward direction, through another one it will move in backward direction. It implies that through both the wires the force that will be in current that will be in mutually opposite direction, so the force that will be repulsive one. Clear to all of you? 4.23. A uniform magnetic field of 1.5 Tesla exists in a cylindrical region of radius 10 centimeter. Its direction parallel to the axis along the east to west. A wire carrying a current of 7 ampere in the north to south direction pass through this region. what is the magnitude and direction of the force on the wire if A, the wire intersect the axis, B, the wire is turned from north-south to northeast-northwest direction, C, the wire in the north-south direction is lowered from the axis by a distance of 6 centimeter. Now see, magnetic field that is 1.5 Tesla. Current passed that is 7 ampere through the wire. Now R that is 10 centimeter for the cylindrical region in which the magnetic field exists. So that is 0.1 meter. Okay. See, if we take the cross section like this, for that cylindrical region, the magnetic field that is inside it, and here this is the wire passed through it. Okay. So here we can understand this thing. If the current is passed through this wire, then the wire when intersect the axis of the cylinder, at that time the magnetic field and the current both are perpendicular to each other. So force that is BIL sine theta, that is theta is 90, BIL current that is 7 ampere, length that is 0.2 given to you for the wire. How we can say 0.2? Because the radius of the cylindrical region that is 0.1. So when wire is passed through this one, so length of the wire which is in the magnetic field that is 0.1 plus 0.1 that is 0.2. Clear? And magnetic field that is 1.5 Tesla sine 91, and you will get the force acting on the wire. Clear? And now as per right hand screw rule, you can understand the force that will be vertically downward. Clear this one? Now question B. The wire is turned from north-south to northeast-northwest direction. So if this wire is turned like this, so then also the length of the wire, which one is in the magnetic field, that is same one 2R, and the magnetic field and the current element IL both will be perpendicular to each other. So here the wire is turned from north-south to northeast-north-southwest direction. The force that will remain same one. Now third question. See, the wire in the north-south direction is lowered from the axis by the distance of 6 centimeter. See, wire is lowered by 6 centimeter. So now here we have to find the length of this part of the wire which is inside the magnetic field. So X that we have to find. This part that is the radius of this cylindrical region. Okay. So R that is given to you. So this is R, that is 10 centimeter. This one is 6. So we have to find X. And the length of the wire which is inside the magnetic field, that is 2X. So from figure, we can write force F that is I into 2X into B. Field and wire both are perpendicular to each other. So no need to write sine 90. It is 1. Now, as per Pythagoras theorem, we can write 10 square that is equal to x square plus 6 square. So x square that is 100 minus 36, that is 64. So x that is 8 centimeter. So 2x that is 16 centimeter. So in that particular case, the force acting on the wire, that is I 2x B, as per that, the current that is 7 ampere, 2x that is 16 centimeter, so 0.16 meter, B, that is 1.5. And now solve this one. You will get the answer. Clear?